Hi everyone, this is Prof. K speaking, and today we're going to talk about the dissolution process, or the process of making solutions. Our learning objectives for today are to determine the basic properties of solutions and how they form, to be able to predict whether a given mixture will yield a solution based on the molecular properties of its components, and to explain why some solutions either produce or absorb heat when they form. So let's start with describing what a solution is. So a solution is a homogeneous mixture of two or more substances. And so on the right-hand side of the screen here, I've drawn a solution and I did little purple dots for the molecules just to show that they're evenly distributed or homogeneous. But in reality, what you'd probably see is this just as a purple solution. I just thought it might be useful to see molecularly how some compound might be dispersed through this solvent. And so the solvent is the component of the solution present at a significantly greater concentration, whereas the solute is the components, one or more, of a solution present in relatively lesser concentrations. So this picture here that I've drawn with color, which you might not see these molecules like this, they should be maybe one solid color, or maybe even you don't see a color. So for example, if we have H2O as our solvent, we could add NaCl to it, table salt, and what you would just see is clear water. And in this clear water, you would have some distribution of sodium and chloride ions. And so that's what we're talking about with a solution, is it's some homogeneous mixture. And in order to be certain that we have a solution, there are some things that we check for when we're seeing, is this actually a solution or is it some other sort of mixture that isn't homogeneous? And so what being homogeneous means is that after it's mixed, the composition is the same throughout. And so what this tells us is if I took a little bit of salt water from the bottom of a container, it should have the same amount of salt and water as if I took a little bit of salt water from the top of the container. It's got the same composition of materials all throughout my beaker. And the components are dispersed on a molecular scale. And so what this means is you won't have six salt molecules clumped together in one part of the solution and 4 clumped together elsewhere. Instead, you have individual salt molecules, or ions if salt falls apart, which we'll talk about in the next video, that are spread out in your liquid. And so they should be individual molecular or ions or whatever we're talking about, but they shouldn't be in aggregates, which means a clump. And if we left our solution out on a desk, we wouldn't expect to come back later and have the material have to be settled out. So one thing I like to think about here is if I went outside and I took dirt and I added it to water and I shook that dirt and water up, for a while you'd see dirty water and it would look brown throughout. But the longer you left it out on a table or whatever, you would see that dirt settle to the bottom. And so that's not an example of a solution. Putting dirt and water isn't a solution, you're just mixing it. So the other thing that we look for with regards to solution is that the concentration of our solution can be varied continuously, with solubility being considered, which we'll talk about more as we move forward. But what this means is if I added a tiny amount of salt, I would have a small concentration of salt in my water. If I added a little more salt, I would have a slightly larger concentration. So we're able to vary the concentration of it and it will still spread out in the material. And typically what we see is that the physical state of the solution is the same as the solvent. And so in this picture provided in the book, when you have potassium dichromate and you add it to water, you end up with a liquid phase that looks like potassium dichromate that has been dispersed in the water. And so this is what we mean by dispersed. And what I was saying about, you probably can't see individual chromates hanging out in the solution. They've just fallen apart and now it just looks orange. They're dispersed, it's homogeneous. And if I leave it on the counter in a week, it will still be this orange solution that we have here. And so how do we know what will form a solution? Or how do we know why some compounds form solutions and others can't? And so one of the major rules is that forming a solution must be a spontaneous process. And in order to describe something as spontaneous, its Gibbs free energy or its delta G has to be negative. And so we're going to talk about thermodynamics more as we move forward, but I found it useful to include it here because it helps me to explain how both the enthalpy or the energy that the system has and the entropy changes that the system experiences can help us predict whether or not something will form a solution. So if we want this whole equation to be negative, then if we have a delta G that's negative, we're more likely to, if we have a delta H that's negative, we're more likely to have a delta G that's negative. And that means that we want this process to be exothermic, or when we mix our material, our solute into our solvent, we'd like it to produce heat because this will help make our process more spontaneous. So this could help us. It's not required, but it's useful. The other thing that we need is we want delta S to be positive, or we want the entropy of our system to increase. And so both of these will help us determine if our process would be spontaneous. But what's actually happening, and how do we know whether it's endothermic or exothermic? Because you might sort of understand the thermodynamics and say, okay, I know we want something to release heat and we want entropy to be positive, but what does that mean? What's actually happening? And so here's the step-by-step process of talking about this dissolution process. So the first thing that you do is you add the solute to the solvent, or you add the solvent to the solute, whatever it is, you mix them together. And just mixing them shouldn't produce anything until they start to interact with each other. And so what needs to have happened if we want to get a solution, is that any solute intermolecular forces have to be overcome. So in other words, if it's going to be dispersed at a molecular scale, then the solute and the solute have to be willing to let go of each other. Otherwise, it's not going to dissolve. You have to break those intermolecular interactions in order to form new interactions between the solute and the solvent. And from the solvent's perspective, it also needs to have some of its intermolecular forces broken so that the solute can mingle with the solvent molecules. And so these two steps of this process are endothermic. And what that means is it takes energy to break apart intermolecular forces. And so this doesn't necessarily help us towards the goal of being spontaneous. This takes energy to break apart intermolecular forces. However, once the solvent and the solute can start interacting and forming attractions between each other, then you have some exothermic component to this process, because now you've broken up interactions and you're forming new ones. And when you form new ones, it helps stabilize the system, which is an endothermic process. And then, because you're dispersing your solute in the solvent, we have increased entropy. And the reason for this, we'll talk a little bit more about as we move into the thermodynamic sections of the course. But what you can effectively think about is as the solute spreads out into the solvent, it has more possible places to hang out. So it's more chaotic and the entropy increases. And so throughout this process, we have a mix of endothermic and exothermic interactions sort of shifting around, and we have an increase in entropy caused by the fact that our molecules are dispersing into the solvent. And so what we think about is, what is the combination here that allows us to be successful or to have this solute? We need to look and see, would it rather have solute-solvent interactions, or does it prefer to maintain its solute-solute and solvent-solvent interactions? And so these are just the same again. Yes, this slide, I particularly wanted to point out that this exothermic process that we have where solvent and solute interactions start is officially referred to as solvation. So this is another vocab word you might encounter, but it basically describes that the solvent is solvating or interacting with the solute. And so if we're coming back to this point, in order for this to be spontaneous, we can think about the different processes I just said, but on an energy diagram. And so if we make this diagram here where this axis is energy, and we have some initial state where we're just mixing the solvent and the solute, and then we have some final state. And so in this system, the difference between the initial and final state, this delta G, is going to be negative. This process is going to be spontaneous. Because in this system, we have where our enthalpy is increasing for our system as we break. So breaking solvent, and breaking solute. So that's endothermic. And then the amount of energy that comes from solvent-solute interactions is this purple line. And then our entropy, so increased entropy this should be T delta S, increased entropy from dispersion. So the combination of all of these leads to enough of a spontaneous process that in this particular system, we would say a solution would form. And so what this represents is that you have some favorable solvent-solvent interactions that we've broken down, and we had some favorable solute-solute interactions that we broke down. But fortunately, the solvent-solute interaction is large enough that it provides some of that exothermic consideration, and our increase in entropy is high enough that we can reach this final state in a spontaneous process. But if I asked you, if you just consider delta H here, is it endo or exothermic? And so in this situation, it is actually endothermic because our final enthalpy and our initial enthalpy here leads to the net need to absorb energy to break down the solute solvent. But because delta S is large enough, it's still spontaneous. And so this is one example of where we would predict a solution would form. And so if I'm thinking about this and I'm saying, okay, if I add one solute that doesn't necessarily have strong intermolecular forces to a solvent that it can interact with the similar amount of intermolecular forces, then it might be the case that even though it takes some energy to break apart the original interactions, there's still a lot of favorability of interacting with the solvent, and being able to spread out increases the entropy enough that a solution would form. And so this is one example where you would predict that you would have a solution form. So I'm going to erase part of this. So pause the video if you need. And I'll show you an example where we might not predict that a solution would form. So if instead we had where we started our initial state, we have some large amount of energy it takes to break up the solute-solute and the solvent-solvent interactions, and we still do get some favorable energy from the solute and solvent interaction, but just a little bit. So it's not particularly happy to talk to that solvent. They don't attract each other, they're not similar. And then our increase in entropy is also only a slight increase in entropy. So maybe comparable to the last one, but overall the sum of these means that when I'm talking about the spontaneity of the system, that overall, this is going to have a delta G that's positive because the breaking of the solvent-solvent and the solute-solute is too endothermic. So this system would absorb energy too much as it tries to break apart these interactions. So these are too strong, and the solute solvent are too weak here. So in this situation, we wouldn't expect for you to form this reaction. We wouldn't expect this to dissolve. We wouldn't expect a solution here. That's the better way to say it, not that it would react. So there's no dissolution here. And so in both of these cases, our delta H is endothermic, which means that for both of these cases, the intermolecular forces that existed before you mix them are stronger than the intermolecular forces after you mix them. It's also possible that the solute-solvent-solute interactions could be weaker than the solvent-solute interactions. So I'll draw that one as our last example here. So I got to erase again. So pause if you need to write down what I wrote. And so now we're going to talk about a system where delta H is exothermic, or where our interactions between the solvent and the solute are favorable. So here we have our initial state, we have our final state, and we have our original endothermic breaking of solvent-solvent and solute-solute. And it might be the case that the solute-solvent interactions are favorable such that I need the purple pen. The solute-solvent interactions are better than the solute-solute or the solvent-solvent. You can have an exothermic delta H. And then when you stack on top of it the improvement in entropy from the dispersion, we get an even more spontaneous dissolution process. And so this is much more favored. So it's possible that you can get dissolution for something endothermic and something exothermic. But if you have a dissolution that's exothermic, it will make it far more likely that a solution can form in these systems. So this is some of the ways that we can talk about how we might predict whether or not something is going to be endothermic and exothermic. And it depends on what the differences are between solvent-solvent interactions, solute-solute interactions, and the resulting solvent-solute interactions. So we'll be practicing comparing those two and seeing how that helps us predict spontaneity for these systems.